Hello! Unfortunately, I lost my lecture recording from Monday's lecture due to carelessly neglecting to check the free space on my voice recorder's SD card. So I ran out. So as a result, I am re-recording the lecture now. In this lecture, I'll finish reviewing the concepts of instruction set architecture that I began last week. Next, I'll highlight a few specific challenges of RISC-V assembly language programming and then show a few simple examples of translating high-level code into RISC-V assembly language. After this, I'll show you the entire instruction set that we'll be implementing in our class CPU by the end of the semester. Then I'll switch gears and talk about fixed point number representation, which is required for Lab 1. And then I'll finish up with two additional high-level programs that I'll translate into assembly language for you. Recall that instruction set architecture is a standardized repertoire of instructions, ways to address code and data, the details of the register sets, and the way to encode assembly language programs into binary machine code. So it's basically everything you need to know in order to program a particular CPU or to build a compiler that translates a particular high-level language to a particular CPU. Microarchitecture, on the other hand, is the circuitry that reads and executes the instructions that comprise programs written for an instruction set architecture. So it's the implementation of the CPU under the hood. Instructions are primitive operations that generally can only perform a single arithmetic operation on values stored in internal CPU registers. Or they can read or write a single register to or from memory, external memory, or they can make a decision about where in memory to fetch the next instruction. They can only do one of those things. There are other types, though, of less used instructions, such as exception handling instructions and I/O instructions, but all instructions are performing the smallest amount of workload that can possibly be assigned by a program to a CPU, which basically means that programs execute a lot of instructions. RISC-V is named after the RISC or reduced instruction set computer approach to instruction set design. And this is where the amount of work that's performed by each instruction is made to be as little as possible, which allows the instructions themselves to be as fast as possible. This comes at the cost of having to require more instructions to be executed in a given program. This is as opposed to a CISC instruction set or a complex instruction set computer, which allows individual instructions to perform more work individually, such as being able to access one or even multiple locations in memory, as well as to perform an arithmetic operation. This has the effect of increasing the time required to execute each instruction on average, but it allows there to be less instructions that need to be executed for a given program. So another way to explain this is if you look at the classic architecture performance equation, which states that the execution time of a program is the number of instructions executed to run that program, multiplied by the time required on average to execute each instruction. CISC CPUs are trying to minimize the number of instructions per program at the cost of higher time per instruction, because each instruction is more costly in terms of execution time. Whereas the RISC architecture is minimizing the amount of time per instruction because they're simpler, they're performing less work, but increasing the number of instructions required to execute a program. That's a trade-off. Since we're focusing on a RISC CPU, you'll find that the fact that you need more instructions to execute a program makes it harder to write assembly code. Sorry. But the good news is that it'll be easier for you to build your processor, and this course focuses on the processor building aspect of it. So don't despair. This is the right approach for this class. The next few slides will compare the MIPS architecture, which you covered in CSCE 212, to the RISC-V architecture that we're using in this course. They're very similar. Both have 32 general purpose registers, with register 0 always containing the value of 0. Even if you write a different value to it, it still will have 0 in it. In assembly code, MIPS used dollar signs, or uses rather, dollar signs to signify a register, while RISC does not use this convention. Both ISAs allow the programmer to address registers by number, 0 to 31. In MIPS, it's $0 to $31, and in RISC-V, it is X0 to X31. Or you can use their symbolic names, such as S0 to S11, T0 to T6, A0 to A7, RA, SP, GP, TP, and 0. RA is return address, SP is stack pointer, GP is global pointer, TP is thread pointer, and 0, spelled out 0, is register 0, which always contains the value 0. These symbolic names represent the conventional usages of various register ranges. For example, S0 to S11 are supposed to be perceived, or rather are perceived to be registers having longer lifetimes. So it is expected that someone writing a function that is meant to be called by other code would preserve the value of S0 to S11 on the stack. So basically, if you call a function, you can expect that your S0 to S11 will not be destroyed by the function you're calling. And then as a function writer, you are expected to save those registers at the beginning of your function and then to restore them at the end. So basically, you're saving the caller's S registers at the beginning and restoring them at the end. You don't have to do that, at least not by convention, for the T registers. So T0 through T6 are temporary registers, and you can expect those to get wiped out when you call a function. SP is the stack pointer, RA is the default register that holds the return address for a function call, and I'll talk more about those a little bit later. Arithmetic instructions generally accept 2 input registers or source registers, and they also have 1 output register or destination register. The destination register is listed first in RISC-V, but that is not always the case depending on which assembly language you're writing. Note that the registers don't need to be unique when listed in the instruction. So in other words, the same register can be used as the source and destination register, or you can use the same register as both source registers, or you can use the same register as both source and the destination. Since arithmetic instructions only perform 1 operation each, when you have a complex mathematical operation like the one shown here that has 3 operators and 4 input values and 1 output value, this is going to require 3 arithmetic instructions to perform with the values that are in the 2 sub-expressions, which would be g plus h and I plus j. They need to be, those sub-expressions are intermediate values that need to be temporarily held in registers themselves. So basically, you have to use registers to store values that aren't necessarily corresponding to a variable in your high-level code. Generally use the T registers for this. Some of the arithmetic instructions have an immediate version of the instruction that allow you to replace one of the source registers with a constant. For example, this instruction adds the constant 4 to the value in register S3 and stores the result to register S3. So we say that we're incrementing S3 by 4 with this instruction. These types of instructions are commonly used for loop control variables. Note there's no subtract immediate instruction, so whenever you need to subtract an immediate, just use an add immediate with a negative immediate constant value. RISC architectures are called load store machines. You might be familiar with that term from 212. It means that they can only perform operations on values that are in the registers. And then you have to use separate instructions called load and store to exchange values between registers and the external memory. There's several ways to address memory with load and store instructions. In this example, I use the .data directive to label a section of this program as an area in which I want to allocate space for global variables and arrays. I added a label for an array called var. You know it's an array because there are multiple values listed there that I'm using for initialization. Then I use, after the var label, I use the directive.word to specify two things. One, that var should be placed on an address that is aligned or evenly divisible by the word size, which is 4 bytes. And the second thing is that the assembler should reserve 4 bytes for each of the initial values listed next after the word directive. In this case, there's 3 values listed. This will cause the assembler to allocate 12 bytes for the whole array. If you don't have initial values for the variable, then you would have to use the .space directive next on the next line in order to allocate space, since if you don't have initial values to put in there. The .text directive labels the text, which is the code section of the program. The first instruction in the program is a load word, and I specify the destination register x2 and the memory address as var. Since var is an array, this will only load the first word of the array in the destination register. The assembler will convert this single instruction into 3 instructions needed to load all the 32 bits into a register containing the address of var, and then use that register as the base register, which is essentially the same as a pointer, and then it dereferences that pointer. So I'm showing those 3 instructions here. The AUIPC instruction is essentially the same as a load upper immediate instruction. The AUIPC is a load upper immediate that also incorporates the program counter. I don't know why they use that one instead of load upper immediate. So that fills in 20 bits, the upper 20 bits of x2. The add I fills in the lower 12 bits, and then x2 is used for the load instruction as a base register. So with 2 instructions, you can initialize a 32-bit value. Notice that they use x2. They recycle x2, which is pretty nice because they, this way this pseudo instruction expansion doesn't destroy any other registers. It basically just reuses x2, which is nice. You might remember from Mars that they would use register 1 sometimes when they would expand these pseudo instructions, which could cause bugs if you were using x1 before that. The next instruction, I used the pseudo instruction LA, which stands for load address, to have the assembler generate the first 2 instructions that I described above. But it leaves out, because it's a load address, it leaves out the actual load part. This allows me to load the address, or to load the value myself, to use the address that was calculated by the load address to do a load instruction. In this, using the load, my load, which comes next, is using the target register of the load address, which is in this case x3, and I use it as the base register in the load instruction. This allows me, this will also allow me to, for example, I could use an offset here. So in the next instruction, I offset that base address x3 by 4. In this case, the 4 is a constant, and this will allow me to load the second element of the array, since the second element is offset from the first element by 4 bytes, because each element is 4 bytes. I can also add the value 8 to the address, as I do in the add I instruction here. and then use the result as a base register, which will load the third element of the array, because I increment my address by 8, which will advance the pointer in x3. It'll advance it past elements, the first two elements in var, and point it to 3. And in fact, this is generally how one performs array indexing in assembly language. That is by loading the starting address of an array into a register, adding a value to it equaling the index value that you want in the array, but you have to multiply it by the element size, which is why I used the offset 4 and the offset 8 there. And then using that value in a subsequent load instruction to load the value that you're indexing. In the case of the stack pointer, or SP register, you don't need to initialize it because RARs will do that for you. This way, whenever you'd like to push data onto the stack, you simply decrement the stack pointer using an add immediate instruction with a negative offset. And in this case, the offset would be the size of the data that you want to push onto the stack. In this case, it's just 4. I want to push 1 word on the stack. Then you use the store instruction using the stack pointer as the base register. And if you're pushing more than 1 word, then you would have different offsets on that store for each of the words you're storing to the stack. In this case, I'm just storing 1 word, so you can see that my offset there is 0. Likewise, when you want to pop from the stack, you perform a whoops, that's a typo. Sorry. I load a load. When you want to pop, you perform a load instruction with the same offsets as when you stored, and then you add the offset. So notice I subtracted from the stack pointer first, and then stored when I wanted to push, and then when I want to pop, I load, and then I add to the stack pointer, which of course is the reverse. Accessing arrays in RISC-V assembly language requires much more attention than it does in high-level languages because there's no hardware support in RISC-V for specifying an index register, nor does the assembler keep track of the size of data types. As a result, the programmer must explicitly perform all address calculations. So take, for example, this simple loop that copies data from one array to another. It copies from source to destination. To do this in RISC-V assembly, you need to initialize registers to hold I, which is the loop counter, but also the index and the index into the arrays, as well as the pointers to the arrays themselves. Now, there's different ways to do this. Also note you have to load the loop iteration limit n into a register, because branch instructions or decision instructions don't accept immediate values. So even if that n were a constant, you would still have to load that constant into a register. N is a variable in this case. So I need to load in this case, S0 is my n in this loop. After these initialization instructions, you begin the loop with a label. And the first thing I do in this case is check to determine if the loop should perform in an iteration. So I use a branch on greater than or equal, comparing I, which is T0, to S0, which is my n. And that's the loop iteration count limit. I'm using greater than or equal, which is the opposite of what the loop said to use. The loop said to use less than, but I use greater than or equal because it is logically opposite to less than, since the high-level code is listing a continuance condition, but the assembly code is giving an abort condition. You could write the assembly code with the same logical expression for the continuance expression, but it would cost additional complexity and additional instructions. So this is the way I simplified it. I basically said, if the continuance condition, which is I less than n, is false, then bail out, jump to exit. The next thing you do in the loop is shift I by 2 bits to the left. That multiplies it by 4, which is converting the value of I into the number of bytes required to hold I words. Note that we could have used a multiply instruction for this, but there's no multiply immediate. So this would have again required more instructions to set up the constant of 4 in another register, so I just simplified that by using a shift to multiply. The next two instructions add the value of I times 4, which we just calculated, it's now in T3, to the base address of both source and destination, which are in T1 and T2, which allows us to subsequently load a word from source of I and then store the same value to destination of I. And then we finally, after that, so there's our load and store, and then we add 1 to I, and then branch back to the beginning of the loop, and that will, after we branch, we'll be checking the continuance condition again. And if the continuance condition fails, then we will branch to exit, or actually I should say if the abort condition succeeds, we'll branch to exit, ending the loop. Notice how the code is formatted into tabbed columns with a column, the first column here for labels, second column for instruction mnemonics, little code word for the instruction. Then you have a column for registers, and then a column for comments. This formatting, the way you format this code is up to you. It's up to the individual programmer, but having a good formatting does improve readability, and reading assembly code is hard enough as it is, so any way you can improve readability, I recommend that you do that. Same goes for comments too. You want to have good comments if possible. I mean, as good of comments as you can put in there. Another challenge with RISC-V assembly language programming is the requirement that the programmer associate every variable with a register. And like I said, in addition to variables, there's also intermediate values too that go into registers. So you have to then keep track of the lifetime of each of those registers, because you only have 32 registers and they have to be recycled after you're done using them. So in other words, not only do you need to remember which register you're using for each variable, but you need to know which registers are in use and which are available for reuse at every point in your programming. Reassigning a register that's in use is the most common type of error that I personally encounter when writing RISC-V assembly code. So here's an example of that. In this example, the line of C code in red involves 3 arithmetic operations and 3 unique input variables B, C, and D. I load the values of B into T0, which means that T0 will effectively be B throughout the segment of code that evaluates the line of C code. After this code is done, chances are I can recycle T0, but I need to maintain T0 as B while I'm executing this line of C code. Likewise, I load C into T1, and then I add B and C, which are now held in T0 and T1. And I store the result of this addition, which is a sub-expression, into T0, which is now an intermediate result containing part of the overall expression that I'm computing. I could have saved this intermediate value into T1, which would have recycled the register that was originally holding C, because I won't need C again, at least not in the code that I'm compiling here, converting to assembly language. So, but instead, I chose to allocate a new register T2. So technically, T1 was available at the point in which I could have used T1 as the destination for that add, but I didn't. I used T2. Next, I load D into T3, and I multiply the sub-expression result in T2 with T3, which performs this part. And then I store the result of that sub-expression, which is not a sub-expression that has parentheses around it, but it is a sub-expression that would need to be calculated as part of the order of operations. However, I made a mistake here. I used T0 to store that product. Why is that a mistake? Well, it's because I was using T0 for B, and if you look at the code, it's pretty clear that I assumed that B was still in T0 because I then use T0 in the next line of code, thinking that I've got B in there. So basically, I've blown away my value of B, and I was going to reuse that because B shows up in the expression twice. So in order to fix this error, I can just change the destination register in the mul instruction to an available register such as T1, T2, or T3, and then of course that would have to be then put into that add instruction as one of the sources. Let's look at another example which adds the values of 4 values that are stored in an array. This is similar to the previous example, but this time I am going to simplify the loop even more by performing the continuance condition at the end of the loop, thereby avoiding the need for an unconditional branch at the top of the loop. This avoids the need for, I'm putting the continuance condition at the end of the loop body as opposed to putting the continuance condition at the top and then having to have an unconditional branch at the bottom branching back to the top, basically. So this avoids me having to have 2 control instructions in here. But this is technically an incorrect translation of the C code because this loop in assembly code will always perform at least 1 iteration. But in the C code, there's no guarantee that you'll always perform at least 1 iteration of a for loop because for loops are a pre-test loop, and I'm doing a post-test in my assembly code. But as an assembly language programmer, you don't always need to perform a literal translation of the C code. And in this case, I'm assuming the code will always iterate at least once, because in this case, the iteration count is hard-coded at 4. So there's no, it'll be doing 4 iterations because I encoded this in the assembly code. This is a slightly modified version of the same loop, but this time I replaced the load instruction with and the fixed iteration count of 4, although I still load 4 into T4. I don't actually use it for anything. But I'm replacing that with a system call that actually reads in the inputs from the console, and it terminates the loop when the user enters a value of 0. So this way a user types in as many values as they want, and the loop will sum them up. I don't check for overflow though in this loop. So I assume the user won't overflow the register. To do this, I use the system call 5 by loading the value of 5 into A7 and issuing the eCall instruction, and then I read the return value from A0. A list of the system calls and how to use them is available in the RARS help menu. This slide shows the 30 instructions that we will ask you to implement in your class CPU. The arithmetic, logical, shift, and comparison R-type instructions, which accept 2 register sources and write the result in a destination register, are all very similar in their functionality since they all do the same thing, differing only in the ALU operation that's being performed. So specifically, there's 13 of these: add, subtract, multiply, multiply high unsigned, set less than unsigned, and or XOR, shift left logical, shift right logical, and shift right arithmetic. Likewise, the arithmetic, logical, and shift I-type instructions have a version that accepts 1 register source and 1 immediate constant value, and again write the result into a destination register. And these are again all similar in their functionality. They only differ in the ALU operation that's performed. And when I say similar in the functionality, I mean they read 2 registers, they do something to it, and they write the result back. There's 8 of these instructions. There's add immediate, and immediate, or immediate, XOR immediate, shift left logical immediate, shift right arithmetic immediate, shift right logical immediate, and load upper immediate. So that gives us 21 instructions so far. Then we've got the CSRRW instruction, which is different in that it is an I/O instruction, and we'll be using it in the class to accept input from the 18 switches on the DE2 board, and also we can use it to output values to the 8 7-segment displays on the DE2 board. So this is how we interact with the outside world. There are 6 branch instructions that are all similar, differing only in the comparison that's being performed. The comparison determines whether the branch is taken or not. And then there are 2 jump instructions which are unconditional. And they both write the return address to a destination register. So that's jump and link register. So that completes our repertoire. In the next 5 slides, actually, I explain the functionality and how to use all of these instructions, and they are also described in a document that is linked on our Dropbox Moodle page, but I want to point out a few oddities here. So there's 3 multiply instructions: multiply, multiply high, unsigned. The multiply instruction works how you would expect in that it multiplies the contents of the source registers and stores the product to the destination register. The problem with this is that many times the 2 32-bit source values will generate a product that requires more than 32 bits. In fact, when you think about it, when you multiply any pair of single-digit decimal integers between 0 and 9, there's 100 possible products. So this is your elementary school multiplication table. But if you count, there's 58 of them, 58 products in the 10 by 10 multiplication table that require 2 digits. So more than half of the single-digit numbers you multiply will give you a 2-digit product. So for this reason, RISC has an alternative multiply instruction, mul-h, and an unsigned equivalent, mul-hu, which stores the upper 32 bits of the product. So this way, if you perform both a mul and a mul-h on the same input registers, you're basically able to recover the full 64-bit product. But you have to execute 2 instructions to do that. The shift instructions in RISC-V are different than in MIPS. RISC-V shift instructions, SLL, SRL, and SRA, use a second source register to specify the shift amount, whereas if you remember in MIPS, the shift amount was actually an immediate value, a constant. In RISC-V, you can use the immediate versions of the shift instructions to specify an immediate shift amount. So basically what that means is that in MIPS you would say SLL, whereas in RISC-V you would say SLLI. In MIPS there was an unconditional jump, the J instruction, which is now replaced by the B instruction, unconditional branch. Note that this is a pseudo instruction that actually maps to the JL instruction. So B is not even a real instruction, but if you implement the JL in your CPU, then you will effectively be able to use the B instruction on your CPU. Finally, I included the load and store instructions in the list, but we're not going to be implementing these in our core CPU, but I list them here just so you're aware of them. Now I'm going to change topics to an application detail that you need to understand Lab 1. Fixed point representation. It's a way to represent fractional numbers using integer hardware. The idea is really simple. So for an n-bit number, and in the case of RISC-V, n is going to be 32 generally, because that's our word size. So you will assume that the rightmost F bits are fractional bits, meaning that they appear to the right of the decimal point, or technically the radix point, since we're talking about binary numbers, not decimal numbers. But I'll say decimal point because that's the term everyone's familiar with. So the value associated with bits, let's say bit n, where n is 0 to 31 in RISC-V, is going from having a value of 2 raised to the power of the nth power, right? So bit 10 has a value of 2 raised to the 10th power, 1024. We're going to change that now with fixed point, and we're going to change it to n minus f power. This means that the rightmost or least significant bit has a value of 2 to the negative f power. This way, the fraction part of the binary value is the value in the fractional bits. If you think of the fractional bits as a field, you're taking that value and dividing it by 2 to the power of f. So in this example, in the slide here, I'm showing a 6-bit number with 3 fractional bits, and the value is, in this second example, is, so there's 6 bits, 3 fractional, so the value here is 101.101 in binary. So the non-fractional part is 101 is 5, so it's 5 point, and then the 0.101 in binary means that the fractional part is also 5, but it's over 2 to the third power or 8. So this is 5/8, and it's 5/8 because there's 3 fractional bits. So the value in here is 5 and 5/8, which is 5.625. The same value, though, if we increase the number of fractional bits to 4, would be different, because then the non-fractional bits would be 2, and the fractional bits would be 1101 in binary, which is 13. And since there are 4 fractional bits now, the fractional part are 16ths. So this is 2, assuming this is an unsigned number. So this is 2 and 13/16, which is 2.8125. Now, I think the part that's most confusing about fixed point is that there's no way to specify the number of fractional bits in your assembly code, or even in C or Java for that matter, unless you're using some kind of a library, fixed point library. So as a programmer, you need to decide how many fractional bits you want, and this is based on the range needed. So the range for a fixed point number is just 2 to the power of the number of non-fractional bits for unsigned numbers, and -2 raised to the power of non-fractional bits minus 1 to +2 raised the number of non-fractional bits minus 1 for a signed, right? So, but the good news here is that for all the arithmetic you do on fixed point numbers, you only need to use integer instructions. If you add or subtract fractional, fixed point values, you got to make sure that those values, the source values, are set up to have the same number of fractional bits. That's all. So if you, generally speaking, you're going to add 2 values, they should have the same number of fractional bits. If not, you have to shift one of them to correct. When you multiply 2 fixed point values, you need to remember that the number of fractional bits in the product will be the sum of the number of fractional bits in the operands. So after you multiply 2 values with f fractional bits, you will have 2 times f fractional bits in the product. And generally speaking, you're going to need to right shift that product after you multiply it by f bits. That will convert it back to having the same number of fractional bits as you had in the source operands. Now, why do you need to do that? Because generally speaking, you're going to try to maintain a consistent number of fractional bits throughout your program. In general. So I give an example here. These values are 45 viewed as regular integers, but they're 2.8125 as fixed point values if you have 4 fractional bits. And if you multiply them, you get the value of 2025 as an integer, but again, if you're in fixed point, you would say, well, I've got 2 inputs that both have 4 fractional bits, so I have 8 fractional bits in the product. And then if you divide the value in those 8 fractional bits in the product by 256, which is, of course, the significance now of the fractional portion, 256ths, you get, 2, 7, and 233, 256, which is 7.914. 0.015625, which works out. Skip this for now. Okay, so Lab 1 asks you to write a RISC-V program in RARS that will compute the square root of a 32-bit input value. The input value is assumed to have 18 fractional bits, and it will return the result as a 32-bit value also with 18 fractional bits. RISC-V has no square root instruction, but so you have to write this behavior into software. But it does have the ability to square a number because you can multiply a number by itself. So this allows you to use a binary search in which you guess at the square root, square that guess, determine if your guess was too high or too low, and then you can adjust the guess accordingly and try again until you find the correct answer, or until you get as close as possible with the available number of bits. Now, one thing I want to note here that I forgot to mention in lecture is when you implement this on the FPGA board, the input is coming in as an integer, so you're going to take the input from the 18 switches and you're going to convert it to have a fixed point value with 18 fractional bits by shifting it left by 18 bits. In this program, however, we're assuming that you actually have a 32-bit set of switches, so the input actually can be a fractional input value into this program. But again, when you put this on the boards later, the inputs will be restricted to being integers, but the outputs will be fractional. So anyway, this is all described in the lab sheet. If you have any questions, please feel free, don't hesitate to contact me or one of the TAs. Now, so what this means is since the range of an unsigned 32-bit number with 14 fractional bits is 0 to 2 raised to the 32nd minus 18th power, or 2 to the 14th power, which is 16,384. Technically it's one less at 16,383. But basically it's 16,384. That's the maximum input value, and therefore the maximum output value would be the square root of that. So the output is going to be between 0 and the square root of 16,384, which is 512. So the input is between 0 and 16,384. And like I said, it can be a fractional number, so it could be 16,383.9999, for instance, right? And then the output value is going to be a fractional number, but between 0 and 512. So you can set your initial guess to the halfway point, which is 256, and your initial adjustment up or down to 128. And every time you square the value of your guess and then adjust it, you will then be halving your adjustment amount. And you'll keep doing this until your adjustment amount goes all the way down to its minimal value, which is 2 to the negative 14th power, which is roughly 4 times 10 to the negative 5th power, I believe. So it's about 4 100,000ths in base 10. And then, that will be your last, that's the smallest amount you can adjust by. So Charles and Philip will provide additional tips and advice in their lab sessions. The lab is due on September 12th by midnight. Okay, switching back to the topic of RISC-V assembly code, I've written 2 additional non-trivial examples for you to consider. The first is a Taylor series approximation of the sine function, which should work fairly well on input values between 0 and 2 pi. Hopefully you've seen Taylor's expansion before in one of your classes, or the Taylor series rather. But basically if you haven't, it's a neat way to approximate a transcendental function like sine, because what you basically do is convert it to a polynomial. If you're not familiar with the Taylor series, you basically, the prerequisite is that you know the value of the function you're approximating, as well as the value of its derivatives for a single input value. In this slide, that value is labeled A. And then once you know that, you construct the Taylor's expansion, and that allows you to calculate the value for any input value, or at least any input value that's relatively close to A. So in other words, if you know the value of f of A, and the value of the derivative of f at A, and the value of the second derivative of f at A, and so on, you can construct a Taylor series. The approximation is increasingly accurate with the more derivative values that you include, but there are limits, because notice that there's this factorial in here that grows very fast. So there are practical limits to the Taylor expansion, or Taylor series rather. In this example, I'm going to approximate sine of x, and I will set a to 0. Now, this is very convenient, because the derivative of sine is cosine, and the derivative of cosine is negative sine. And not only that, but the value of sine of 0 is 0, and the value of cosine at 0 is 1. So these two things really simplify this series, and basically it makes it collapse down to x minus 1 over 3, 1 over 2 factorial. I'm sorry, yes, x minus 1 over 3 factorial, rather. Sorry, I was right the first time. Times x to the third power plus 1 over 5 factorial times x to the fifth power plus minus 1 over 7 factorial times x to the seventh power. So basically, you're alternating signs with these sub-expressions, and you're increasing the denominator by 2 is odd numbers, and then of course you're taking the factorial of the denominator, and you're increasing the power of x by 2, and those are also odd numbers. Since the range of sine of x is only -1 to 1, positive 1, we're going to try to get away with having 2 non-fractional bits internally. This will leave 30 fractional bits. 30 fractional bits allows us to represent a value as small as 2 to the negative 30th power, which works out to be about 10 to the negative 10th power, which allows the smallest factorial inverse, right, to be 1 over 13 factorial, which limits the Taylor series to having 7 terms, 13 divided by 2. So this slide shows my C-based implementation. Notice I wrote my own factorial and exponentiation functions, and as well as my sine function, which is a approximation of the sine using the Taylor expansion. The factorial routine, which is shown in this slide, is a straightforward loop similar to the previous example that I showed. It works by initializing the variable val, which is held in t0, to 1, and then looping n times, multiplying the iteration count inside the loop body by that val, t0. In this case, I don't perform a pretest on the loop, since I know all my factorials will have an input value of no less than 1, because I'm the one calling the factorial function. I don't trust anyone else to call it, and I trust myself to not put a value in there that's less than 1. And then I copy the value of val of t0 to a0. A0 is, by convention, the return value for a function in RISC-V. My exponentiation function works in a very similar way, except there's a catch here. The problem with the Taylor expansion is that the 1 over factorial terms are obviously going to be giving you very small fractional numbers, while the n to the power terms are going to give you large numbers. So if I calculate these terms separately, I'd need to keep track of 2 different fixed point format, one of which would have more non-fractional bits and the other one would have more fractional bits. To solve this in a simple way, my exponentiation function takes as input as one of its inputs. It takes obviously x and the power of x you want to raise. But it also takes the value generated from the 1 over factorial value. And it uses this as the starting point. So normally if I was exponentiating, I would start with 1 and I'd keep multiplying 1 by x, and then I'd multiply that product by x, and I multiply that product by x until I've gone through a number of iterations equaling the power, or the exponent, I should say. But instead of setting the initial value to 1, I'll just set the initial value to 1 over the factorial value, which I already calculated. So that way I start out, instead of starting out at 1, I start out at the value that I would be multiplying by this exponentiated value, or anyway, inside the Taylor expansion. So I start out with a very small number, and then I just keep multiplying the value of x against it for n times where n is the exponent. This way, both the intermediate values and the return value can all keep the 32-bit, 30 fractional bit fixed point format. Now, unfortunately, it's still required that I retain all 64 bits every time I multiply, meaning, so I'm having to use the multiply and the multiply h instructions. Since the input value of x has 30 fractional bits, and I'm multiplying against that by x, which has 30 fractional bits, so that each intermediate value is going to have 60 fractional bits in the product, so I have to shift. And by the way, I just realized here too, because I've chosen 30 as the number of fractional bits, the input value is also restricted to being between 0 and 4, although technically it's actually, -2 to +2, because it is signed in this case, and I know it's signed because I'm using the mul h instead of the mul hu. So I mentioned earlier the input value would be between 0 and 2 pi, but in reality, because of my fixed point format, the input value would have to be between -2 and +2. So keep that in mind. Now you can fix that easily just by adjusting the constant frac bits that I have listed here, and the comp frac bits is simply just 32 minus whatever that value is. So keep that in mind. This is why it's important to consider your fixed point format, although in Lab 2 we're telling you what format to use, so you don't have to consider it, at least for Lab 1. Okay, and the next 2 slides show the sign function and how I perform the 13-point Taylor expansion in a loop. I'm not going to go through every instruction. It's fairly straightforward. I added comments and as well as the corresponding lines of C code that I used. The code is also on Dropbox if you'd like to download it and test it out. And feel free to ask any questions you have about it. Okay, and then I'm going to show you one more example, which is a merge sort. The merge sort is a recursive algorithm, which when written in assembly language requires that you use the stack to store local variables, and you're going to notice that the result of this is that there's a lot of stack accesses in here, although the stack accesses themselves are not that complicated, but they do add a lot of instructions. The merge sort is very simple. You just take an input array, you split it in half, then you call the merge sort recursively on both sides, and then when those return, you can assume that both of those halves have been sorted, so then you just have to merge them together by walking through them and choosing one element from either half and putting it in the output array. So this picture is actually showing how the merge sort works using the actual input data that I used for testing my code. The C implementation is shown here. You can see those values are up there in the data. You can see that it's actually very short. The size 1 and size 2 variables are very important since they define the size of each of the halves. You might say, well, shouldn't that be the same? Well, no, because if there's an odd, if the variable is an odd size, then these will be different. So if it's for example 7, I'll have 3 and 4 in there. Also, data 1 and data 2 are local variables. They have to be put on the stack. They're actually local arrays rather, and they're holding the two halves of my input data, which originally are unsorted, but by the time I'm done with this function, they will be sorted. I'll be returning, I'll be sorting those and then merging them and then returning the result of that merging to the caller. Now the tricky part here is to allocate these arrays on the stack. How do you do it? It's actually very easy. At the beginning of the merge sort routine, you decrement the stack pointer by the size of the array, which, as you can see, I just use an array size of n, which is more than I need if I'm only looking at half the data, but it'll work. And then once I decrement that stack pointer, I just keep that stack pointer in a register basically as a pointer into that part of the stack. And then I do it again for the other half for data 2. And then once I have those registers, I can just store to them as base registers, and I'm storing to the stack. I can also pass those registers as input to recursive calls to merge sort. Notice that the merge code, which is over on the right-hand side here, it just walks through the output array, copying one element from either one of the halves. So A and B keep track of where you are in each of the halves, while the I variable keeps track of where you are in the output array. So nice and simple. Now the only challenge there is if you reach the end of either data 1 or data 2, you have to stop looking in that array. So that's why we have this if then else statement here. This is probably the trickiest part of the code. The test array is shown here. The code begins here. Notice that we halt the system to end the program, system call 10. This stack shows the stack pushing code. So as I mentioned, there's a lot of stack pushing and popping instructions. So I have basically a whole slide for that, but it's pretty simple. Remember, to always save the return address, so you can go back to your caller if you're planning on calling another function. This slide shows the initialization of size 1 and size 2. This shows the copying of the first half of the data into data 1. This shows copying the second half of the data into data 2. This is how we make our recursive call to merge sort. This is where we begin the merge loop, and this is the end of the merge loop. And actually, there's actually 3 slides as the merge loop. And again, that's mostly because the big if then else condition needed to deal with conditions where you finish copying data from one stack or the other. One half or the other. And then that's the stack pop code. And that's it. So I realized I went through this very fast. I tried to put enough comments in there to make it self-explanatory. I think if I were to explain every instruction, it still wouldn't be as effective as you looking through it. So the point here was to not expect you to be able to do this complexity of a conversion, but it's intended to show you how constructs in C and in high-level languages in general, at least procedural high-level languages, are translated into assembly code. And also to show you my coding style, in which I wrote everything in C first, and then I included all of the C code as comments in the assembly code. Because otherwise it's very easy to, well, even then, even doing all that, it's easy to make a mistake, but it becomes almost impossible to write assembly code without that. At least it is for me, although you may be a better programmer than me. So that's it for this lecture. I will see you next week. I'm sorry for forgetting to, or not forgetting, but losing my recording and then taking extra time to post this lecture. If you have any questions, please contact us. We'll see you in lab this week, and I will see you in lecture on Monday. Thank you.